Hello, you're welcome to my channel. My name is Silo, and in this video we're going to answer this question right here. Why is it that when we take the derivative of e raised to the power of x, we get back e raised to the power of x? In other words, why is it that the rate at which this function e raised to the power of x changes at any point on the x-axis, okay, is the same thing as the value of the function evaluated at that point? Another way you can interpret this is, why is it that the slope of the tangent line to this function e raised to the power of x at any point on the x-axis is the same thing as the value of the function evaluated at that point? Okay, well, this function right here, based on that property, is 1 in a million. That is, it's a very interesting thing to know, that you differentiate a function and you get back the same thing. Okay, so before we dive right into it, let me say this. In one of the videos I posted some years ago, I tried to evaluate the limit as, let's use x here approaches infinity, okay, of 1 plus 1 over x raised to the power of x. And after everything we got e. But that isn't cool. The reason is, well, the method, everything we did it as a naive, as a naive method, we did it right. But it doesn't make sense. It's secular reasoning, because this right here is not something to be proven. This right here is actually a definition of this number, the Euler's number e raised to the power of 1. This is how it is defined. So you don't evaluate the limit to prove definition, because we don't prove definitions, but rather we use definitions to prove mathematical theorem or other propositions. Good. So I shouldn't have done the video. Okay, but I'm just bringing this up because it's going to be helpful right here as a definition. Again, we will not prove it because it's a definition, but rather we use the definition to prove some other theorems or to make some other derivations. Okay, good. And just to add to this, this is a more general case than the first one. It's a more general, not actually the general. Okay, so and that will be the case where this place is replaced with t. That will be the power of e. Okay, that will be helpful in this video anyway. I just wanted to point that out. Okay, so back to this. So let's think about this function e raised to the power of x. Maybe let's graph it a little bit to see what we have. So let me graph it right here. So we just have the graph of the function. Okay, so this is our axis, the x-axis, and then the other one was the y-axis. So let me put it out here, the x-axis, and since in this case I'm going to use the y-axis, okay, so let's just put the y-axis. We want to graph the function e raised to the power of x. So let me put the curve right here. Well, it's just a sketch, okay, so you're just going to go up like that. That's how it looks like. Good. So this is the function y equals to e raised to the power of, that's e raised to the power of x. So you put e raised to the power of x like that. Now where this thing touches the x-axis, that is where the y-axis, that is where x is equals to 1. So you notice that's where x is equals to 0. If x is equals to 0, the output is just going to be 1. So that's what we have. Alright, great. Now this is the curve. Now again, from what I talked about the derivative of a function is just the slope of the line tangent to that function at a single point. So let's say this is a single point. And let me call that point an arbitrary x on the x-axis. That's by dragging it like this. So you want to find the slope of the tangent line. Okay, in other words, the slope of the line tangent, that is the slope of the line that touches this curve at that single point. So let's put it like that, assuming that's the tangent line. So you want to find the slope of this tangent line at this point. That is the line that touches this curve at this single point, x. Well, the coordinate, the corresponding y coordinate of that point is going to be, when we substitute x into the function e raised to the power of x, of course that's just what we're going to have, e raised to the power of x. Okay, so I'm just taking this x as some arbitrary x. I don't want to use x naught. Okay, yeah, so just permit that anyway. Okay, but how do we find the slope, okay, at a single point? You know, using this point slope formula where we have y2 minus y1, that is the rise, divided by x2 minus x1, that is the change in the x-axis. We'll need 2 points, but here is just a single point. How is that going to be possible? So let's say we don't really know what to do there, but this is what I can tell you. Well, since we know how to find the slope of a line that touches the curve at 2 points. That's when 2 points are given. In other words, the slope of a secant line. So let's think of another point on that curve, okay, and then let's draw a line that cuts across those 2 points, and this line is called a secant line. That is a line that cuts, a line that touches a curve at more than 1 point. So that's a secant line, okay? So you just understand that. So, good. So let's say that's the secant line. Oh, it doesn't fit in very well. Let's put it out here. Okay, I hope I've gotten that okay. Good. So that's the secant line. So to find the slope of that secant line, we'll just take the slope of the secant line is given by, well, let me get the corresponding axis. So this right here. So let's say that this point, okay, horizontally speaking, that this point is some distance away from the first point on the x-axis. Let's say it's h distance away, such that this right here is going to be x plus h. Good. So this second point is going to be this x plus this distance. This is just the horizontal distance plus h. That gives us this other x coordinate of this point. Then the corresponding y coordinate is going to be e raised to the power of x plus h, okay, because we just added h to that to get this new point. Good. So these 2 points will help us to find the slope using the point slope formula, which is given by the rise, that is the change in this axis, that will be e raised to the power of x plus h minus e raised to the power of x, then divided by the run, that is the change in the x coordinate, which will be x plus h minus x, which is going to give us h. So using the point slope formula, the slope of this secant line, so let me just say slope, let's use m for the slope of the secant line. So let's write SEC is going to be the same thing as, well, this right here, which is e to the power of x plus h minus e raised to the power of x, that's the rise, divided by the change in the x coordinates, which is h. Good, that's the slope of the secant line. But that's not the main aim. The main aim is to find the slope of the tangent line at this single point, which is called the derivative, that is the instantaneous rate of change. Well, how can we achieve this tangent line? Okay, so you think about this other point, this second point, as being flexible enough so that you can move it along the curve y equals to x. If that is the case, so I suppose that we move this along this curve towards this tangent point, that is this point of tangency. What will happen? Well, as you move it along, this horizontal distance will be shrinking, will be getting smaller. So we move it along such that the slope of the secant line becomes the slope of this tangent line. In other words, this horizontal distance will become smaller and smaller so that it approaches 0. So this is what I'm talking about. So if we think about this yellow line as coming like this, okay, maybe cutting like that. So in this case, this point has been brought down so that it is now here. I know the work is getting dirty. Good. So we can push it downwards again and again until it gets closer and closer to becoming this tangent line. In that case, this point here will be getting closer and closer until it gets to this point, this point of tangency. Okay, in other words, giving us the slope of the tangent line. Good. So what I'm saying that is that the slope of the tangent line, then let me use the slope of the tangent line, which is the derivative, is what we're looking for, is going to be the same thing as the limit as this horizontal distance h approaches 0 of the slope of this secant line. Good. But the slope of the secant line is given as that. That means that the slope of the tangent line, which again is the derivative, so I'm going to like to write that as a derivative with respect to x of the curve e raised to the power of x, okay, is going to be the limit as h tends to 0 of this right here, which is e raised to the power of x plus h minus e raised to the power of x divided by h. Okay, so since we want to verify or want to find out why this is equals to that, so let's say we know the result, but we are just going to verify. So we're going to evaluate this limit to see if it will give us that. Good. So in the next page, we're going to write this limit and then we're going to see what we're going to do. And don't forget this right here. So let me put it out in the next page. Okay, so we're going to evaluate the limit as h tends to 0 of a raised to the power of x plus h minus a raised to the power of x, right? Good. Divided by h. Okay, and also from what I said, we take note that e raised to the power of t is given as, okay, so that just over there. Anyway, let's continue with this. Well, you notice that in here or up here we have this right here, which we can write as e to the x times e to the h. Okay, using the fact that when the bases are the same, we can add the powers. Okay, just indices, some index rules. All right, so this is going to be the same thing as the limit as h tends to 0. Now, using that, notice that this right here is also e raised to the power of x. We can factor that out. That will be e raised to the power of x. Then in here we're going to have e raised to the power of h minus 1 divided by h. So I'm going to pull this out of the limit because it is independent of h. In that case, this will become e raised to the power of x out here times the limit as h tends to 0 of this fraction. But I'm going to write this fraction like this. I'm going to put the denominator as 1 over h, then e raised to the power of h minus 1. But based on this definition, what is e raised to the power of h? Is going to be this definition where the t will be replaced with h. Okay, so in that case, we're going to have this to be e raised to the power of h. Okay, is going to become the limit as u tends to infinity of, now that will be 1 plus t, but in this case t is our h. In our new case, t over u, sorry, I shouldn't be writing t, I just said t is h in our case, so that will be h over u. Good, that is raised to the power of u right there. Okay, and notice that this is minus 1, then we subtract 1 from that, and then we close that right there. Alright, so let's evaluate that to see what we have. Well, I'm going to work out the limit. I'm going to work this inside out. So this limit as u tends to infinity of this inside. So you notice that in here we have this binomial this binomial 1 plus h over u, alright, raised to the power of u. So we're going to expand this binomial, alright, using the binomial theorem, and then we're going to try to simplify things and then see what we have from there. So just a quick one, this is going to be 1 plus, well, that is h over u times u, that is the binomial theorem, then plus, well, we're going to build up the power, that will be u into u minus 1 divided by 2 factorial times the square of h over u. Good. And then we can continue infinitely. The reason is this u, this the power here, is approaching infinity, so that will continue infinitely. All right, so I'm not going to do all of that. I'm just going to stop there because I can make a good enough observation that will help us. Okay, so let's see where this limit leads us. So this is the limit as u tends to infinity, that is u. Okay, all right, so this is 1. Now notice that 1 minus 1 will cancel, that is 1 minus 1 will be 0, so maybe I will not write the 1 over there again. Then also notice that the u cancels out with u, leaving us with h. So that is, this is h right here. Then plus, well, in here I'm going to write the 1 over 2 factorial like that. Then notice that u into u minus 1, that is u squared minus u. Then in here, or over here, we have h squared over u squared. So let me bring the u squared inside to divide each of these terms. Okay, and then outside there we just have h squared, and then we can continue like that. The next term will be the h cube over u cube term, and then this will be 3 factorial, and then this power will just keep on. Okay, that continues infinitely. Okay, so let's see what this will give us. Now, this limit will become now the limit. Oh, sorry about that. That is the limit as u tends to infinity of, now this is h plus, now this is 1/2, or 1/2, yeah, that is 1 over 2 factorial. Let me just put the 1/2. Then in here we have u squared over u squared, that is 1 minus 1 over u, good, times h squared. So what happens as u tends to infinity? As u tends to infinity, this is independent of u, that is just h plus, now this right here will be breaking down to 0. As u tends to infinity, this will become 0, leaving us with 1/2 times h squared times h squared, and of course, sorry, this is supposed to go on infinitely, so that is plus dot dot dot. That is what we get. Now this should continue to h cubed term, h to the fourth power term, and so on and so forth. That's the dot dot dot, right? But that is just the limit inside. So I'm going to rewrite this function. That will become, so this right here, maybe let's call this equation 1. So 1 becomes, right, that becomes e raised to the power of x times the limit as h tends to 0 of, now 1 over x times this inside. Well, this inside is what we have here, so that will be 1 over h times what we just simplified to get, that is h, plus 1 over 2 h squared, plus, and so on and so forth. Okay, plus, and so on and so forth. Good. So what happens is that this h squared, this h outside, will cancel out with this one here, leaving us with 1. Then it will cancel out with one of this h, leaving us with h. Okay, so this guy here becomes e raised to the power of x times the limit as h tends to 0. So let me just write it out here. The limit as h tends to 0 of, now here is 1 plus, that is after this and that cancelled, plus 1 over 2 times h. Sorry, this is 1 over 2 times h. Alright, now what happens as h tends to 0? This term will be 0, leaving us with just 1. So the limit of 1 as h tends to 0 is just 1. 1 times e to the power of x is actually e raised to the power of x. And this right here is the limit, which we said that the limit, okay, which is e raised to the power of x, what we've just done on the other hand, is the derivative of e raised to the power of x as x tends to, the derivative of e raised to the power of x with respect to x. That tells us about the instantaneous rate, that is the rate at which this function changes at any point on the x-axis, and that is what we have. So that is why whenever we say the derivative of the natural exponential function with respect to x, this right here stays the same when differentiated. Okay, I hope that was fun. If you like the video, please don't forget to subscribe to my channel, share the video with your friends, and we'll see you in our next video.